All right, the next part of what we're going to talk about are heat, temperature, and how they contribute to the atmospheric motion. So we got all this energy coming into the Earth. We need to distribute it. It can't stay all hot down at the equator or all cold up on the North Pole. So how does temperature change? Where do we get it to move from? So what are some of the causes that transfer heat? So temperature, what is it? It's kinetic energy. In other words, it's molecules in motion. Believe it or not, all the molecules that exist in the air, on even in things like furniture or wood or solid concrete, they move. And the faster they move, the more kinetic energy they possess. So molecules that are in fast motion have a higher temperature. And heat is just energy in transit. In other words, if I have two objects near each other, and energy is flowing from one to the other, that's heat moving from that new other object. And that is creating what's caused that kinetic energy we talk about. So, for example, a temperature gradient. In other words, if I have a strong cold front coming through in the wintertime, and at one moment in time, temperature is 60 degrees outside, 20 minutes later, it's 32 degrees. That was a temperature gradient. That was temperature changing. So in other words, heat had to be moved in through the system. There was a gradient that occurred. So there are different ways that heat flows: radiation, conduction, convection, latent heat. So let's explore a few of those. And also, heat always flows toward lower temperatures. So in other words, even if it was a cold front, the heat energy is flowing back across that cold front to the cold air from the warm side. Radiation we've been talking about, it can move energy through anything such as a vacuum, even other air, whatever. So, and you think about it in a convection oven, when you have radiation or whatever, microwave oven where it's emitting microwaves, heating up the food, that is heat from radiation. So here's conduction. Conduction, if you ever don't want to, but if you touch the hot stove or whatever, the heat transferring into your hand, which your hand is colder, uh, would be conduction. In the middle of summer, for example, when you might be out there and see a very dark surface and it's a very, very hot day, that surface is getting very hot, absorbing heat, energy, radiation. If you were to put your hand or some water on it or whatever, the heat would be transferred immediately from that surface into that other substance, and that is conduction as well. Convection. Ever watch water boil? You can see the little bubbles coming up. That's convection. Convection only occurs in a fluid, such as a gas or a liquid, and the atmosphere isn't gas. So it has convection within it. Basically, warm air rises, cold air sinks. You can see the circle here. Sensible heating just as conduction and convection together. Latent heating. Heat is released when water changes state. In other words, when water melts, freezes, etc., something happens with heating. So, since water is the only gas in the atmosphere that can change its state, it is one that controls a lot of latent heating. And we have a lot of water out there with all the Earth's surface, 70 some percent of it being covered by water. So, latent heat is absorbed from the environment. You can see it here. If something melts, it's releasing latent heat. Basically, you're always going to be, if you're going from a solid to a liquid to a gas, latent heat is being released. If you're going the other way, from a gas to a liquid to a solid, it's absorbing latent heat. So that is just the simplest way of looking at that. So Ocean. It's a great source of latent heat, has a lot of water, and it is very high sensible specific heat. So it takes a lot of energy to warm it up. Uh, I'll give you my example here that I like to think about with Virginia Beach, close to where I live. During the fall, that water's sitting there at 69, 70 degrees for a lot of the fall. And it heated up into maybe close to 80 in the summer. Now, over the winter, it'll drop back into the 40s. It will take, even though the air temperature is sitting in the 70s, maybe starting in early April, the water temperature is going to take till May to June to warm back up into the 70s. All because of how slow it heats. And if you live near a maritime climate, it can really impact the amount of temperature change you get. In the middle of the country, temperatures change a lot. There's not a lot of marine influence. In other words, if you're living in Ohio, for example, temperatures are going to get much stronger cold times and much stronger warm times. If you're living on the West Coast, even though San Francisco, you would think, would get a lot of cold air, the ocean keeps it steady. So you wind up getting a milder winter and a cooler summer. Here is just an atmosphere, how the energy and the radiation and all the various aspects of it. Then you can see there's a lot of different components to the radiation and how it's been working. Here's conduction and convection. In other words, for example, if you have a cumulus cloud forming, there's convection that lifts heat up into that cloud. So it moved temperatures up, raised the temperature in the cloud, heat was transferred into it. Now, at that point, if the temperature in that cloud causes condensation, in other words, gas becomes a liquid because it's cooled, well, we've just changed state, so latent heat is also released at that point. So as the cumulus cloud's growing, it's gaining heat from below, from convection, conduction, and it's also gaining heat from latent heating. So it's interesting how that transfers all that heat from the ground up and in through the atmosphere. Here is just why heat's got to move. There's a deficit of temperatures in the polar regions and a surplus down from a lot of the equator. So all that radiation is moving towards the north, basically, or towards the south. Air masses are just big volumes of air that all have typically the same temperature and humidity. The air doesn't move a lot in the middle of an air mass when it's forming. That's why it gains these characteristics. So this imbalance of radiation, heating, and cooling, it means air's got to move. It changes some of this into kinetic energy because the air starts circulating. This causes our various seasons, why we have storms, all of that. If you were to look, for example, at one given day here, we would have overnight no incoming radiation, so we're losing infrared radiation, so it's cooling. Some point in the morning, the sun comes up, and the radiation from the sun starts exceeding the radiation leaving the earth. So the temperature rises. And that's why in the afternoon our max temperature typically is, because the air rose until it reached the same point where the infrared and the ultraviolet radiation are equal. So when you have a bare surface without a lot of water on it, or none, what happens is that surface absorbs a lot of the solar radiation and allows it to reheat the air. That's what happens in the desert. Say it rained at your house a lot. The next day, the sun came out. What's that energy from the sun doing? It's releasing that water vapor, is causing it to evaporate. So some of the energy from that sun is going into evaporation instead of into heating the air. So the air stays colder. Now you have things like high albedos, like a lot of cloud cover sitting over top of your house. The clouds are reflecting the sun's radiation, so it stays a little cooler. You can see all these different things come impact to try to figure out what your temperature is going to be. And here's just an urban heat island, for example, in Washington, D.C., where there is so much heating takes place right there in downtown because of all the concrete and everything, holds in the heat, releases it back out. So I wanted to show you, here's a surface weather map right now. Temperatures are always the upper left corner on the surface weather map. So, for example, this air mass formed up over Canada has made its way into partway across Ohio. Temperatures are in the 70s on this side, in the 80s on the other side. Same exact thing over the East United States here. Notice all the east winds here. The east winds are coming off the Atlantic Ocean, keeping the air colder. Actually, you can see where they stayed colder on the east side of the mountains than on the west side. The air from the Atlantic Ocean did that, the maritime climate. Now, let's take a look. Current temperatures right now. And I wanted to look specifically down around Mansfield. We're on the north side of the front, so we're in the colder air. So this is a 72-hour map of temperatures and relative humidity, dew point. So here's middle of the night a few days ago. Temperatures have dropped down to 62. Relative humidity went up. We'll understand why that occurred later. Right here, temperature 73, and the relative humidity stays high even during the day, all the way through here. My guess is it was raining during this time. Clouds were up there keeping the temperatures down. And then we begin to drop off even more, probably from a cold front going through, and nighttime radiation drops it down into the 50s. Now the sun came back out, the temperature started warming back up again and drying out because the cold front brought drier air with it. So you can see this reflected in just one location, all these aspects coming together to rule. So if you have any questions about this, please don't hesitate to ask.